What happened? Can I get a sound check?
Yeah, you're good.
Huh, why is my camera not working? Oh, no. Just 1 second, guys. Well, I don't know. It's always a struggle. Nope. No. Sorry, guys. The camera's not working, but my dog is working. Using dial-in. Okay, share content. Oh, a couple minutes to spare, right? Oh, no. Okay, guys, let's get started. So let me just sort of again give a brief review of where we were with transistors. So I think I forgot to mention this. It's only, I guess, interesting from a historical point of view. I don't know if it'll help make sense or not, but of anything. But I always thought it was kind of cool that, you know, transistors, or somehow it's short for trans resistance. Trans resistance. And I guess initially, this is like, you know, when in the 40s or whatever, when they came up with these devices. So, you know, the idea I think initially was to have a control input. Okay, guys, sorry. I think my dog's not gonna let us be. So if you just give me 1 second, I'll go draw the curtains and I'll be right back. Just give me 2 minutes. Thanks. Okay, guys, sorry about that. So anyway, so this is the idea behind a transistor, or original idea was that you could get basically a control input that could control, you know, control a resistance between two other nodes. So you could sort of think of it as something like this, I guess. And that, you know, the idea would be a trans resistance in it. I think it was more maybe like a MOS transistor or something like that. So in our case, obviously, we don't have this variable resistor, we have more like a variable current source. So if you can think of this as a control input, we basically have a current source that we are, changing given the input. Okay, so that's the word transistor and where it comes from. And then I know this whole business of looking at the transistor as like something like this. This current, which would be K times V. V is this. V out's here, say. So I remember this whole thing really confused me, and I think it was Kevin asked last lecture about what's why isn't what does this mean? As this thing is just sort of like floating here, it's not connected to anything. Why is that, or how does that make sense? Well, I guess there's a couple of ways to look at that. And this confused me, so I don't want you to. It's probably going to still confuse you guys, but let's just try to explain it. You can think of it as two ways. One of them is that you have this, actual semiconductor device that, is like an NPN transistor. So you have an N, you have a. So actually, if I draw it like this guy, draw it vertically. So if I draw it like in the same orientation as the circuit, it'll be like something like that. And if I call this node the base, this node the emitter, and this node the collector, what it would look like is collector, base, and emitter. So this thing on the left is like a circuit model of something that in fact is fairly complicated in real life. So you can just think of it as a circuit model. The other way you can look at it is because this model is only valid when we have this very specific operating condition for this device. And that is to put make this a positive voltage from the base to the emitter. So, typically you might see 0.8 volts. And then have also a positive voltage from the collector to the emitter at the same time of 1 volt, say, or more. So 1 volt plus 1 volt or more, okay? And what that does, this 1 volt makes the difference between these two nodes. I was going to draw that as a dashed line. So if you had a battery here, this difference would be 0.2 volts, meaning that this guy here is forward biased, this PN junction. And this PN junction here is reverse biased. Reverse biased. And in fact, the reason, if you're looking at why, I think Kevin's actual question, why is there no connection between these two nodes? It's really because the base to collector junction is reverse biased. So if I was going to draw what this circuit would look like under reverse bias, it'd be really, if you guys remember, under reverse bias, what we had was like a variable, like it was a capacitor essentially. So base collector capacitor, which, you know, if we get that far, we'll see that, you know, you actually have that. It affects the circuit when we're looking at the frequency response of the circuit, but not quite now. So essentially, just a long way of saying that the reason there's no connection between the base and collector, no resistive connection, is because this PN junction is reverse bias. So this is really, this circuit model is really just for this particular configuration with these voltages, with these type of, so with this guy forward biased and this guy reverse biased. And in fact, so this is what we had here in this NPN junction, where we would basically, again, put this guy in forward bias, put this guy in reverse bias. And if we have this very specific type of function, and I'm going to go through this really fast. So, you know, again, this is one of those things, there's a lot of detail. So you just need to know this at like a very basic level. So what happens if we have a forward, if we just look at this junction, it's forward biased, meaning again that there is current flowing from the P to, there's whole current flowing from the P to the N region, and there is electron current flowing from the N to the P region. And because this region is much higher doped in N type, so we said the N plus, the number of donors here is much higher density than the number of acceptors in the P side. So basically we're assuring that the electron current is going to be much higher than the hole current. And this comes from, so going back to, I think, let me, should I put this over here? So this goes from equation 2.97 of the book, equation, yeah. So this is going back to a forward bias equation, forward bias junction equation. And the current there was proportional to, I'll just write the whole thing. I just want to, in case you guys were struggling to remember why the currents would depend on the dopant concentrations. Exponential of VF over VT minus 1 plus N sub D over exponential of V0 over KT, exponential of. So this is from chapter 2, talking about the forward bias current flow across a junction. And you notice this is the forward voltage, forward bias voltage, which is the same obviously for the P and the N side. This is the built-in potential, same for the P and N side. So basically what you're left with is basically the whole current is proportional to the number of acceptors in the P region, and the electron current is dependent on the number of electrons in the N region. Okay, the concentration of, dopant concentration in the N region. Okay, so by doping, this is what the people in the factory have done. They've made this N sub D here. This is like N sub D. This is N sub A. They have made N sub D much, much larger than N sub A to make sure that this current in electrons is much bigger than this current in the base. Now, why are they doing that? Well, it's because, like I mentioned, so you want to have what you're trying to do is, or just redraw it here, is a situation where you have a control signal basically modulating a current source. Okay. And when you do something like that, it's much more efficient if you're not drawing. So very little current here can manage a very large current here. So a small current here can vary a big current here. That's like a very efficient transfer function is the way to look at it. So this current, this is the input essentially, as you'll see, of the transistor in this mode of operation. So this is the current coming from the input, and you don't want that to be high because whatever's driving the circuit will have to source that current. And you want that to be low compared to the current that you're controlling, which is this emitter current. Okay, so, and you do that by making this much higher doped than the P. So that's the purpose of that. Okay, the second thing you do, or the people who make this bipolar transistor have done to make a good bipolar transistor, is they have made this, the base region, very, very short. So if I call it, I don't know, the length of the base is very short. Like physically, it might be, one times, I don't know what it might be, but maybe 1 times 10 to the -7 meters or something. So 0.1 micrometer, maybe even shorter. Maybe it's 0.01 micrometers. It's very small. So what that does is it makes sure that the electrons going from the N plus to this P side here, they get injected in close enough to this reverse bias junction. Remember, so now remember, this guy's reverse bias. So now we got to talking about this. What this does is it injects, this junction is injecting electrons into the base. Okay. This junction is preventing holes from coming in here. But this junction, if electrons end up here, this junction will actually pull in those electrons towards itself. Okay, remember very initially we said that if we had a junction that was, wait a minute, this is VF. So we want to make this higher. Yeah, so this is a reverse bias. I don't know why it's called VF. That's usually I would think of it as forward bias, but this is a reverse bias junction. So this is the P. No, sorry, what am I saying? No, you want the N to be higher than this. So this is maybe drawn badly. So if you draw something like that, what happens is if you get electrons coming in, they basically get swept into the N side. So if you look at this side here, is if we get like this junction is reverse bias, so it's preventing holes. It's preventing holes from getting here. But if you have any electrons here, basically they get pushed by the electric field across. Again, remember this is reverse bias, so there's positive ions here, there's negative ions here, so there's an electric field pointing in this direction, and that electric field is gonna, because the electrons are negatively charged, it's gonna pull the electrons over here. So if this base is very short, these electrons coming into this side of the junction just get swept into the collector. Okay, so it basically looks like, so this is kind of what it looks like. The electrons leave the emitter because this width is very short. They get swept in by the collector and go out. So basically what it looks like is we have a very small input current or voltage, depending on how you want to look at it, controlling a much larger current going to the output. Okay, so this also explains why This guy's called the emitter because it's emitting electrons. And this is called the collector because it's collecting the electrons and taking them to the output. Okay. So anyway, that's the basic operation in this mode called this is called the forward active mode. Which is base emitter junction is forward biased. And the base collector junction is reverse biased. Okay, so that's how basically you get this operation, small current controlling a very large current, or you can think of it as a small voltage controlling a very large current. Okay, so no, I'm going to sort of skip through these details. These are in the book. They talk about how the electron density changes inside the base, etc. I don't think for us it really matters much. I think the important things to remember are that the emitter is much higher doped than the base. The base width or length, depending on how you look at it, is very small. And basically you have a small voltage across this base emitter voltage is modulating or controlling a very large current from the emitter to the collector, a very large electron current. Okay, so basically what you end up with is an equation like this as your endpoint. Sorry guys, my dog found something else to bark at. I'm not sure what. Unless we have an intruder in the house. By the way, any questions so far? There's probably lots, but are you guys no questions?
Professor?
Yeah, what's up, Nelson?
So one side's the emitter, the other side's the collector.
Mhm.
What exactly is the collector collecting, and what exactly is the emitter emitting?
Sure. So the emitter is emitting electrons, and it's emitting these electrons into the base. And the collector is collecting those electrons from the base and taking them out to the outside.
Okay.
So
it's current flow.
It's current flow. It's electron current flow. So remember, this guy kind of models like this. This side is the emitter. This is the base. And this is some current source that's controlled by the base emitter voltage. And this is the collector. So basically, this base emitter voltage is controlling a current from the collector to the emitter. If you look at it from a circuit standpoint, this is kind of what we wanted to get. Does that make sense?
Yeah.
And remember, we wanted to get this because if we put an external resistor here, we can get gain out of this circuit. So here, if we put a resistor on the collector, as you'll see, we'll be able to get gain out of this circuit from the input to the output. Any other questions, guys? Okay, so let me just say, so this is if I draw this from a circuit standpoint, remember the bipolar trend. So we have this guy, I'll draw it in the same orientation, N, P, N plus. So this is the emitter. This is the base. and this is the collector. So if I draw the circuit version of this, it's going to look like this. These two are exactly the same thing. Just one of them is, so that, you know, this guy's sort of like a circuit version of, so this is a collector, of what actually gets built is this NPN junction. And in fact, this transistor, sometimes you hear it being called NPN transistor. Sometimes you hear it called a bipolar transistor. Okay, and then you basically put them both into this mode that's called the, if you want to put it in, so I'm going to draw what a forward active mode looks like in red. Forward active mode is you bias the base higher than the emitter. This is almost always around 0.8 volts. Now this collector to emitter voltage could be 1 volt, it could be 3 volts. It needs to be high enough that this guy's in reverse bias, the base collector. Notice that the higher the collector is with respect to the base is 0.8 volts from the emitter. So if the collector is 1 volt from the emitter, the collector is 0.2 volts higher than the base. If the collector is at 3 volts, then it'll be 2.2 volts higher than the base. So it's still in reverse bias, it's more reverse bias. And then if I just draw the same thing here, the base and the collector emitter VCE is, you know, 1 volt or 3 volts or whatever it is. Okay, so if you do this, if you hook it up like this, what you'll end up with is a circuit that looks like this. There's a I sub C here. So this is a current source. This is collector, emitter, and base. And this collector current is, this is the equation, which is dependent on a bunch of stuff. Again, I'm not going to get too much into it. It's the kind of stuff you recognize from the diode. This is the area of the junction, charge of an electron, intrinsic carrier concentration, diffusion constant, width of the base. So like a bunch of, you know, bunch of stuff. But basically people, when you get a data sheet from a transistor, basically they sort of, all that stuff gets bundled into a single value called I sub S. So when I write I sub C is I sub S exponential of VBE over VT minus 1. Okay. Oh, this is the guy here. Which looks a lot like our diode equation in forward bias. Okay. Do you guys recognize that? So if you had a diode, connected like this, the diode current in forward bias would be I sub S exponential of VD over VT. No, whoops, I always put this parentheses in the wrong place. Minus 1. So it's over here that I sub D is I sub S exponential of VD over VT. Okay. And now if you have a, what we basically gave ourselves this transistor. Now we have, basically this is what the voltages look like. So VBE is between these two nodes. And, we're measuring the current going through here. Okay, and now we're saying that I sub C, the collector current, is going to have, similar look to it. Exponential of VD over VBE, VBE minus 1, which looks, exactly the same, right? And if I was going to plot VBE versus I sub C, I would get a very similar current to the diode. In fact, exactly the same current. Okay, so I guess, the question here maybe you should be asking is, well, okay, then why did I bother making this transistor if I was already getting from the diode, I'm getting this same exponential function. Now look at the difference between the transistor and the diode, and it's a critical difference when it comes time to building circuits. The diode is a two-terminal device. That means I had to put the voltage across the diode to get this exponential variation in current with voltage. Whereas in a transistor, I'm putting, because I have it 3 terminals, I'm putting that voltage across, I'm calling it an input, but across 2 terminals. And the current variation is something I get from a 3rd terminal that doesn't need to be connected to here. Okay, so basically I've separated my input from my output. And that's a sort of a critical thing with a transistor. It's a 3-terminal device. I can independently inject an input voltage here and modify the output here. Whereas in a diode, the voltage is connected across the device. So if you want to look at the output, it's basically got to do something else with it if you want to get a working device. But so this is what makes this really powerful, is the separation from the input, which is a controlling signal, to the output, which is what you're changing, which is, in this case, is a current. It's always a current, whether it's a bipolar transistor or a MOS transistor. Okay, this is the important equations for a transistor, which looks exactly like the diode equation. Okay, and this current source I sub C is exponentially varying with your VBE. That means if I put sort of going back a couple of lectures, if I put an external resistor here, R sub L, and call this my V out, and put a voltage source here called V in. Okay, my V out is going to be this current I sub C. It's going to be minus that current, because remember the electrons are flowing out of the collector. Electrons are negatively charged, which means positive current is going into the transistor, into the collector. Okay, so the V out is minus R sub L times this I sub C. So it's R sub L times this exponentially varying current. And again, think of this is kind of a real powerful thing, is this output voltage is being controlled by an input voltage that's totally independent of it. And there's an exponential relationship between the input voltage and the current, or this V out now, right? It's really between the current coming out and the VBE, but because it's getting, it's going, that current flowing through a resistor, there's an exponential relationship between the input and the output. That means like a tiny change in the input can cause a very large change on the output, which is exactly what we want. We want gain. So this is, it's a very like definition of gain. So a small input change gives very large output change. I guess this is as an aside, we can come back to this later, but if you want more current, for example, from a transistor, you can put them in parallel. And as long as they're fully in parallel, it's as if, remember one of the terms here in this I sub C, before we put it all into this I sub S is the area of the emitter. So if you put multiple transistors in parallel, let's say you have a transistor in the lab, it's not giving you as much of a change in output current with input voltage, you can just sort of gang them up together and put them in parallel, and it's as if you have a wider device or more of a current variation with the input voltage. Okay, so any questions up to that point?
Yeah, just a quick question. So
Yeah.
I saw that it was negative RL, so that's still higher than what we had as our input.
Yeah, so this is the one thing that you so let me go back to our first slide. It's almost always when you make transistor-based gain circuits, your gain ends up being negative. That doesn't mean, so there's a difference between negative gain and attenuation. Okay, attenuation means the output is going to be, the amplitude of the output is going to be smaller than the amplitude of the input. That's what not negative gain means. All negative gain means is the output has got a negative polarity compared to the input.
Okay, thank you.
Okay, so if the input's going high going, the output's going to be low going, but with a higher amplitude than the input.
Okay.
Yeah, and it's it is like one of the sources of confusion. But as I was saying last time, basically you just kind of put this out of your mind because kind of everybody knows what's going on, and what you want out of this is gain. And usually, actually, you take these amplifier circuits and put them in a configuration called negative feedback, which is very counterintuitive, and it only works because the transistors or these circuits have gain and negative gain at that. That really does wonderful things. I won't get into what it does now, but you might have, I don't know if you've heard negative feedback, not in the context of tests, but like in the context of circuit design. But like so anyway, long story short, don't let that bother you. It means that you're still getting amplification, but the polarity of the amplification is reversed between the input and the output, and it is not attenuation. Okay. Any other questions? Okay. So let's keep the confusion going. So we drew this. This is one last bit of I'm sure there'll be more confusing stuff. So we drew this circuit like this, right? Now we've been drawing our circuits like that, like this kind of thing, and we've been putting, let me put this resistor from here to here. Okay, so this is the the current that's being controlled by the input. But we can only draw things like this because we don't have to, you know, when we draw a current source, okay, we don't care where the current comes from. Okay, this current is not clear where this current. It just looks like I'm changing this current here, but where's the current coming from? Well, like you have to source these electrons have to come from a supply of electrons. So like that emitter has to pull those, when the emitter emits electrons, in some sense, it's pulling those electrons from the ground. From the ground, now it's pulling those and dumping them into the collector. Okay. So, but you know, when we draw a simple current source, it's like a perfect device, and there's no concept that it's that it needs current from a ground or something like that. But in reality, the current does need to come from somewhere. So the reality of the circuit looks actually like this. If we're going to actually build this circuit in the lab, this would be something that previously we described as like this. Notice where the resistor was. Okay. But in reality, you really have to connect the other side of the resistor. What you really have to do in the real world is connect this resistor to a voltage. Okay, which is what this is doing. So this is the collector. This is the emitter. And this is the base. Okay, and you basically are getting your output voltage from here. So this is your, if you put your input will be here and your output will be here. So this node is equivalent of this node is over here. Okay, basically what I'm saying is in real life, you have to put the resistor, the side of this resistor up and put the voltage in through that. Okay. Any questions about that? So this is kind of the real circuit you guys will be building, hopefully in the lab or whatever, going forward. Okay. Can't believe you guys don't have any questions. It must be that you're very confused. Confused or no questions? Or very obvious? Okay, I'll stop asking.
I
Okay.
need time.
Huh?
Processing.
Yeah, it's got to sink in. I didn't understand any of this until grad school, to be honest. I was just sort of like doing route work.
Just processing.
Yeah. Homework problems helps sink it. Okay. So let's see, where are we going with this? Okay, so let's look at the various things. So when you have, remember we said we have 3 terminals. Actually, let me go back to here. So this is the base, this is the emitter, and this is the collector. Okay. Now, we only had 2 terminals across a diode. So we only had one graph to make. Okay. There's only one voltage and one current. Now, in this case, in the case of the bipolar transistor, I only drew you guys the base emitter voltage versus the collector current. But we have a third voltage, right? We have the collector emitter voltage, sorry, a second voltage, collector emitter voltage. So we could also draw that versus I sub C. Okay, because now it's, you know, the thing is, it's sort of like should be a 3-dimensional graph, because when you think about it, you could simultaneously vary or the collector could vary, the base could vary, and I sub C would vary. So you have, you know, basically a three-dimensional graph. But we're only dealing with two-dimensional graphs. So what we do is we draw the base emitter current, the collector current versus the base emitter, assuming that, so this assumes the collector emitter voltage is at a constant value. That means that theoretically, if the collector emitter voltage goes to another constant value, this curve might change somewhat. We won't talk about that right now. And then the same thing here. If I draw the collector emitter voltage, this voltage, with respect to the collector current, I'll have to assume that I'm keeping the base emitter voltage constant. Okay, so each curve here will be a different base emitter voltage. And so remember that this on our output is a current source. So if I have the collector and this is I sub C. So basically I'm drawing this curve here is what happens if I take a current source and vary the voltage across it. Okay, so that's what I'll be drawing here. And if you guys remember, the very definition of a current source is something that has constant output current regardless of the voltage across it. So if I was going to draw this thing, VCE versus I sub C, it'll just be a straight line. So theoretically, no matter how much I change VCE, no matter how much I change this collector emitter voltage, the output current is going to stay the same. Okay, because this output current, this I sub C, is extremely dependent on the base emitter voltage, you know, exponentially, but not very dependent at all. In fact, you know, in this first order, it's not dependent at all compared to the collector emitter voltage. And the reason I stopped it here is, as we'll see in a little bit, is that's only true for a certain range. So as long as this base collector voltage, as long as this VCE is high enough to keep this junction in reverse bias, basically the collector current is not going to change with VBE. But as VBEs change, so let's say we have a VBE of 1, if I have a different VBE, so VBE of 2, I might get a different collector current. Because remember, this collector current is very dependent on the VBE value. So these are curves where I'm basically holding, so for this curve, I'm holding VBE constant and VBE2 and modulating VCE and seeing no change, but it's at a higher current value than another VBE current that's at a lower value. Okay, so that's what we're looking at here, is when we're looking at the, you know, if we hold the base emitter voltage constant at V1, and we're looking at the collector emitter voltage versus current, it's going to look like a constant value as long as this is in forward bias region and this is in reverse bias, as long as we're in this forward active region, okay, which is this region here in terms of voltage. When this voltage, the collector emitter voltage, if this voltage gets too small, at some point this is stop being reverse biased, and we'll see what happens over here. So something we don't want to happen happens. But as long as we keep it there, basically it acts like a good current source, relatively speaking, with a current value that's dependent with this exponential relationship to the input. Okay. So that's another point of confusion. So again, just remember we have basically two voltages, the base emitter and the collector emitter, and most of the time we're only concerned about the collector current. At some point we're going to start looking at the base current, but it's only sort of as a parasitic, let's say. Okay. No, hey, it's here. So the base current. Okay, so now the base, we said there's a very small base current flows into the base and from the base to the emitter. Remember this base current was going here, and there was a corresponding electron current that was much higher going from the emitter to the base. Okay, so if you look at the base current, it's much, much smaller than the collector current. And in fact, there is a ratio between the two. So another way to look at it is I sub B is the collector current divided by beta, okay, which is a function of this beta is a function of ratio of emitter N sub D's, or emitter donors and base acceptors. So remember I wrote up this, where was it? Yeah. So remember I wrote this equation from chapter 2, and there's basically almost all of this. This is the emitter current, essentially. It has to do with the doping concentration of the emitter, and this is the base current. Okay, and basically this ratio between this and this decides what's the ratio between the emitter and the base current. And since most of the emitter current becomes the collector current, I can just say that it's the collector current. Okay, so basically we have this thing, and then beta, you'll see, so in it, if you buy a bipolar transistor, you'll see for the most part two important things. And one of them is the beta. The other one is the I sub S that we talked about. Which is this guy that goes into the equation as a multiplier. And this beta is usually, I don't know, it's between 50 and 200. So it's like a very big ratio between the collector current, which is your output signal, and the base current, which is, you can think of it as a leakage current controlling the input, which is what makes this an efficient device. So you can think of it as a very small base current is controlling a very large collector current. Okay, so typically beta is given to you, like usually in a problem, I sub S and beta are given to you. Okay, but that's basically the ratio between these two. Okay, so if we were gonna basically, you know, the emitter current is basically just the sum of the collector and the base current, because this is the base. This is the base current. This is the emitter current. And this is the collector current. So the emitter current is just this, is basically the difference between these two. Actually, the base current's really flowing out. So let me actually draw it that way. Because it's, the emitter current is really a whole current. So emitter current is the collector current minus the base current. Okay, so basically these are all the three currents that, and the three equations that you kind of have to remember. You really only have to, well, anyway, so these are the three you have to remember. This is all in forward active mode. Which again means that base emitter is forward biased, or again, typically 0.8 volts, but basically forward biased. And the collector emitter is +1 volt to +3 volts or higher. So this guy is forward biased. This guy is reverse biased. So if you make sure that's all the case, then the collector current has got the exponential relationship, same as the diode that we talked about this. It's the collector current is exponentially dependent on the base emitter voltage. Okay, so this current coming here is exponential. This current is exponentially dependent on this voltage. Okay, if I just look at the base current, is this I sub C. Okay, notice this guy is the same as this guy, just divided by this term beta. And beta, usually in this class, beta is a constant. And usually it's given at 100, but you have to just keep an eye out. In reality, so this is in class. In reality, it might be anywhere between 50 and 200 or something. It could vary more. It just depends on the design of the transistor. Okay, and then the emitter is just the collector minus the base. Okay, and when you calculate it out, it just ends up being that. So basically, this is really the two things you have to remember. This equation for I sub C and the fact that the base is I sub C divided by beta. So I sub B is I sub C divided by beta. And this I emitter is I sub C minus I sub B. Okay. So as long as you're in your forward bias, those are the equations that you have to worry about. Okay. And so now to add the model of this base. So initially, remember, we had this. We had a current source here. And we didn't have anything here because we were ignoring the base current. Now we're drawing a diode between the base and the emitter, and the current of that diode is I sub S over beta. Okay, because it's beta, it's the the collector is, so just write these things down, is equal to I sub C. Okay, the collector current is I sub S exponential VB over VT. This current from base to emitter is beta times smaller. And again, this beta is usually in the class will be 100. Unless I'm told otherwise. Okay. So this basically represents the small leakage current from the base to the emitter. Okay, this is the collector current. This is the actual signal value. And the emitter is basically keeping track of both of those guys. They're both basically kind of sort of flowing in or out, depending on if you're thinking of electrons or current into the emitter. Okay, any questions about that?
Professor, I was looking at the slides as well, and And this picture, especially, it looks like they're being added, but you said it was IC equals
Yeah.
IS,
Yeah.
or yeah.
Yeah. I would, this is the problem, is that it just sort of keeps going between definitions of like how a current flows and how a current doesn't. Like basically that, if you're looking at I sub B being defined as, an electron current or hole current, etc. I guess I would just call these as, just call it the same. Sorry, I think I was making it too complicated. I would just call it basically add the two. Okay. Don't worry about the subtraction, because I think this being a whole current is making things, that's going to make things.
Oh, okay.
So just think of it as
Okay.
as just currents that add. I think so. This is correct. Sorry. So just think of it as two currents that add, the collector and the base, and becomes the emitter.
Okay.
Yeah. Sorry, I was getting too much wrapped around the axis with the deep axle. Sorry, with the details. So you can basically think of the emitter current as just adding these two currents as defined by these two equations. Thanks for clarifying that. Any other questions, guys? Okay, so let's do an example here. So let's just sort of try it before. Let's see here, which is basically this guy. Okay, so it's asking us if we had a sure how all the info. So 0.8 is 500 ohms. This is 2 volts. Does this have all the info we need? I think we also need an I sub S value. Let's pick, I don't know what the book has, but let's pick 1 times 10 to the minus 14 amps. Let's see what that does to us. Okay. Anybody want to volunteer for me to figure out this voltage here? So this voltage, V sub C.
Is it 1.2 volts?
1.2? How did you figure that out?
I did the subtraction of the collector minus the base because it's in a reverse bias, right?
Yeah. So now you gotta be careful here. So now notice we don't really, this 2 volts is on this other side of this resistor. The 2 volts isn't here. And in fact, there's a collector current flowing here. So there's like a voltage drop across this 500 ohms. So you don't, this is not going to be 2 volts. We don't know what it is, but it's 2 volts minus. So if I say what's this VC is 2 volts minus I sub C times 500 ohms. Does that make sense? If I had drawn this, I think what you were saying would have been true if I had drawn this like this, like I guess I have been doing. So trying to deceive you guys. So if I'd drawn it like this, then this voltage, yeah, would have been, the delta would have been 1.2 between this and this. But because I wanted to turn this into a gain element, I added a resistor here. And now we have to actually calculate what this is. So once you help me do that. So we have VBE, right? And we have I sub S. So we should be able to calculate I sub C. You remember what the equation was, Ellen, for I sub C?
Let me see. It's beta times I of B.
Okay.
Would that work?
Yeah, but then you don't know IB either.
Oh, IS exponential of
Yeah.
VBE over VT. That one. Okay.
Exactly right. So VT is 26 millivolts. VBE is 0.8 volts. And then I sub S, I blindly chose it at 1 times 10 to the minus 14 amps. So let's see what this does to us.
Professor?
Yeah.
Where'd you get VT from?
VT is our old KT over Q.
Oh, okay.
6 millivolts at room temperature.
Gotcha.
It's like exactly like the diode equation. So I'm just doing the thing here, exponential. Let's see. So this ends up being 2.3 times 10 to the 13th. This guy is 1 times 10 to the minus 14. So 1e to the 14. So this ends up being 230 milliamps. Man, I really, boy, 230 milliamps. I picked a really bad value for I sub S. Let me pick a smaller number because I think this is going to screw this up. So I'm going to pick another number. This is a better number. 1 times, let's do 1 times 10 to minus 16. So this current doesn't end up being so large. 2.3. Let me do it all over again. So 0.8 volts divided by 26 millivolts, exponential. Thanks, Arthur. 1e to the 16, change sign, multiply. Okay, so you get 2.3 milliamps. Did I get that right, Melvin?
Yes, that's exactly what I got.
2.3 milliamps. Okay, so now basically we have 2.3 milliamps going through there. And this is the equation for V sub C. Okay, so V sub C is 2 volts minus 2.3 milliamps times 500 ohms. So this is 1.15 volts. So this is equal to 2 volts minus 1.15. So this is
0.85.
Thanks, 0.85 volts. Okay, great. So, okay. So we have 0.85 volts here. So we are really close to, so now if I have 0.85 here at the collector, the base is at 0.8. So there's only a 50 millivolt reverse bias across this device. It's still a reverse bias, but it's not a lot. Okay, so now imagine if I had picked 600 ohms as my resistor. If I had picked 600 ohms, it would have this voltage drop would have ended up being what, like 20% higher, and this guy would have come out of reverse bias. So the aim of this exercise, I guess, was to show that as the resistor value increases of this guy, as that guy keeps going up, as long as I have the base emitter voltage constant, the current I sub C is going to be constant. Okay, that means as I increase this resistance, this voltage, this node is going to start getting lower and lower and lower. This is the V sub X. So this is this voltage, meaning that it'll be harder and harder to keep this guy in forward active. So out here is this guy. Notice, at least in this example, I don't know what I sub S they were using, is at this point is when you hit 0.8 volts, which was our starting point here. So if you go any further than this, like this area here is trans Q1 is not in forward bias anymore. So basically you have to be really careful about what value pick for this resistor. Now remember, this resistor is setting our gain, right? Remember that the gain value here from the input to the output is basically I sub C. So V out is I sub C times R sub L. So if I have a certain I sub C, I can increase my gain by, so let me just do this, is I sub S exponential of Vn over Vt. Let's just say this is Vn. So basically, let's say I have a certain input voltage. So this current is defined. Okay, and I want to keep increasing my gain. I could try to do it by increasing R sub L, this value, just so that's the other piece of the gain. But if I keep increasing that to keep increasing the gain, at some point, I'll no longer be in reverse bias. So basically what this exercise is saying is there's a maximum value for gain that you can get for a certain base emitter voltage, sort of supply voltage pairing. Okay, at some point, you're no longer going to be able to have a gain. Okay, so there's a maximum basically gain you can get. Okay. Why don't we stop here, guys? I think I've already probably saturated you guys with info, and I'll put up some homeworks, problems tonight or tomorrow to give you guys some examples to try, and hopefully they'll help sink some of this in before we keep going at it on Tuesday. So let's stop here. Any questions?
Professor, I have a
Alright,
question.
Yeah.
Go ahead, Kevin.
Oh, you could go ahead. It's fine.
All right, I was just gonna say, so we can basically look at as a transistor as essentially a switch that is dependent on the input voltage. Is that correct?
Yeah, you could think of, yeah. I mean, you could think of it as a switch. Right now, we're using it as kind of a more subtle instrument. We're not switching it completely on or off. So you're right. If you were building a digital logic gate, which we'll look at in a bit, you can think of it as a switch because you're either fully turning it on or fully turning it off. So it'll be that, in that sense, it'll be a switch. In this case, we're turning it on or more on or more on. So it's kind of like a analog or a smoothly varying gain circuit. But you're right. In some modes, you could just think of it as a switch.
Okay, thank you.
Did that make sense, Melvin?
Yeah, it did. So it's more like, you know, a potentiometer maybe.
Yeah. There you go. It's like a potentiometer, except instead of like your thumb or whatever twisting something, it's an input. Well, that's a great way to put it. It's like a voltage sort of modulating that. Yeah. But somebody else had another question. Was it Nelson? Who was it? No.
It was me, Professor. I have
Okay,
a question about the emitter current.
Yeah.
So, oh no, I mean about IC. So IC is dependent, or it's going to be influenced more by the voltage of the base emitter than
Yeah.
the.
Up to a certain point. So if you look at, so this is I sub C versus VCE. And you see that as long as VC is high enough, the collector emitter voltage is high enough, I sub C is like not at all affected by it. Okay, this is the collector emitter. But if you're, let's see where we had this. But this is the relationship between the I sub C and VBE. So it's very strongly dependent on the base emitter voltage, but hardly, like basically not dependent on the collector emitter voltage to the first order, as long as it's in this forward active mode.
Okay, that makes sense. Thank you.
And it's so like, so imagine if you were gonna like, because the collector is the output node and the base is the input node. So it would be like a really hard circuit to analyze if the output nodes, if the changes to the output node, we're also changing the current in addition to changes to the input node. You just really, what you really want is the input changing the output current and not the output. If the output voltage was changing the input current, which it does to a little bit, as we'll see, it like makes it really like a difficult circuit to analyze or use.
Professor,
Yeah.
I have a question about that example problem.
Uh-huh.
So I was just wondering, so if we were to remove the resistor on that problem,
Yeah.
would it make it in forward bias then? Or like, yeah, like that was.
I mean, let's draw it out. So let's draw this guy. So I remove the resistor, and what do I connect here on the collector side?
Like, don't you just go to like the VCC
Like that?
thing? Yeah,
Yeah. So now in this case, right? You have forced this node to be a certain voltage. You've forced this node to be a certain voltage. And now you do have, you can force this into being forward bias, like you're saying, or forward active mode. So what was your question? Your question was,
Oh no, I was just trying to understand that. So basically, the reason why this should be in the question is, like the reason why there's the whole like if the resistor gets higher, then there won't be a forward bias eventually. Is it because the voltage drop across the resistor, and so if the resistor is higher, then I mean the voltage on that node is not going to be high either.
exactly, that's exactly right. That's exactly,
Okay, that makes sense. Yeah, I was just trying to understand that.
yeah. Any other questions? Okay, guys. Have a good weekend. Take care.
Thank you, Professor. You too.
Thanks.
Thank you, Professor.